Hello and welcome to the first of 3 lectures that I'm giving on a new theory in quantum mechanics known as Tetryonics. My name is Kyle. I'm a 3rd-year electrical engineering student here at UBC. So the majority of the work that you're going to see here, and as well as in these slides, is not actually created by me, but by the author of the theory, Kelvin Abraham. So he is a guy from Australia. Now Tetryonics is a little bit difficult to describe, but at its core, what it is it's a redefinition of physics in terms of geometry. So what ends up happening is that we're going to see that Tetryonics makes essentially all the same predictions as this standard model, but for completely different reasons. As a result of this, unfortunately, we're going to have to spend a lot of time relearning familiar concepts now in terms of geometry. But as we're going to see, this gives us a more descriptive and more useful description of many different processes and systems that allows us to essentially extend our theory beyond where it currently is and create many new and interesting applications. So Kelvin likes to say that the language of physics is math, but its grammar is geometry. So geometry describes the rules of what it makes sense and does not make sense to say in terms of mathematics. Some very simple examples are the electrical resistance of a circuit element, where we have it proportional to the length and inversely proportional to the area. And some of you may be familiar with the idea of boundary conditions used for solving partial differential equations. So over the course of this lecture, we're going to see sort of a bird's eye view of the general ideas in the theory and how it works. And we're going to get this through deriving the periodic table. Now this is not a real derivation because it's based upon essentially a gigantic amount of assumptions about what energy is and how it behaves. But in later lectures, we're going to go into more detail on all the processes we see here tonight. And we're going to see why these assumptions were good ideas. But to start with, we're going to begin with the initial, most important assumption, and that is energy is a literal thing with a real geometry and dimensions. So what you're seeing up here is 2 sides of a single quanta of energy, the smallest unit of energy that can exist. So we describe these as an equilateral triangular coin. So it has 2 different sides and 6 different components. On one side, we have a positive electric field pole and a corresponding north-south magnetic dipole. On the opposite, a negative electric field pole and a corresponding south-north dipole. So we describe these quanta as perfect quantum inductive loops. For those of you familiar with electromagnetics, we know that a changing electric field is going to create a magnetic field, and a changing magnetic field is going to create an electric field. So we say that what we're seeing here does not actually all exist at the same time. This is a time average of all the different field components of these quanta over a single period. We have this electric field grows in strength and area, and it creates this magnetic field. As this magnetic field is created, it creates this electric field. As this electric field is created, it cancels this positive field and creates this south-north magnetic dipole, which then in turn recreates this positive electric field. This process continues forever and no energy is ever lost because these are perfect quantum inductors. Over the course of these lectures, we're going to see that this 2-dimensional geometry is a simplification of a 3-dimensional system, and that this is a frequency domain analysis of what energy is doing at the quantum level. We have 4 additional core assumptions about energy. The first is that energy will only be stable if it joins in as part of an equilateral geometry. Square numbers of energy correspond to these equilateral geometries. Energy in all its forms will seek to expand to its minimum possible density and reach equilibrium. And the last one is that the universe is an energetic system in an eternal state of dynamic equilibrium. So a continuation of our first 2 assumptions is what Kelvin calls the learning to count triangle. So when we want to describe larger systems comprised of more energy, we have to create a larger equilateral triangle out of many smaller equilateral triangles. We're going to see that we can use this single geometry to basically describe everything in physics. And that's not an exaggeration. We're going to see everything from quantum mechanics to general relativity and special relativity. So this geometry has a couple of very important mathematical relationships in it. The first is that it has to grow in odd-numbered steps as well as decrease. So if we go down this triangle from the top, we see we start with 1, we add 3, then we add 5, and then 7, and 9, and so on and so forth, as seen on this left-hand side. So it grows in odd-numbered steps. If we count up the total number of quanta that we have in any geometry of any size, we see that it's always a square number. If we start with 1, 1 is a square number. If we go down to 4 total quanta, 4 is a square number, and so on and so forth. So we can see that this total number of quanta in this geometry is equal to the number of rows that it has squared. And we're going to soon connect that to scalar measurements, whereas the row number is the vector measurement of, say, like the energies of motion of a particle. Another important relationship that is going to be very important at the end of this lecture is that the vertical columns of the energy in this triangle create a very special distribution. So we start on the right here and we have 1 quanta in this column, then we have 2, 3, 4, all the way up to 9, and then all the way back down to 1. At the end of this lecture, we're going to connect this to uncertainty in quantum mechanics as well as probability and statistics, and show that this geometry actually creates the standard normal distribution as well as all of the uncertainty properties of particles. The next assumption is that when these quanta join together, they join like this. So this is what we call inductive coupling. Now this doesn't entirely make sense because what we have is a north pole binding to a north magnetic pole. And we would think that they'd want to repel, but this is just an assumption that we're going to make for now, that it's actually stable like this. And we're going to see, especially during the last lecture, why this is actually a good thing. But as a simplification for now, we can essentially say that these positive and negative electric fields are attracted to each other and they bind together. So we can see that on this side of this large geometry, because these are all energy coins and it has 2 sides, we have +1 electric field, because red is positive, for every row. We always have 1 extra red than the black, because red is on the exterior edge. So whatever is on the exterior edge actually determines the polarity of this side of this geometry. But because these are triangular coins and they have an opposite side with the opposite polarity, this geometry has no net charge. Another important assumption we're going to make is that while we also technically have no net magnetic field, we're going to say that there is a net magnetic moment across this geometry from one side to the other, pointing from north to south, because we have this separation of these magnetic poles on either side. And we can see once again that the size of this magnetic moment is proportional to the number of rows in this geometry. So as a result of our third assumption, that energy wants to expand and reach its minimum density and seek equilibrium, we interpret this as meaning that each one of these quanta has a velocity associated with it. And this velocity points from the base of the triangle to its tip. As a result of this geometry, we once again see that we have 1 net forward velocity for every row. We also know that these quanta are quantum inductors. The energy circulates and oscillates between its different components inside of these quanta. So while the net velocity of this is only equal to 1, 2, 3, 4, 5 quanta of velocity, which is much less than the speed of light, so this entire geometry is going to move at a finite and very small velocity. What occurs is that the energy bound in this geometry as it oscillates is going to travel at the speed of light within this geometry that it's constrained inside of. So we can think of this as essentially a traveling standing wave. A good analogy as to how this behaves is that this is something that can move across the floor by vibrating. So these magnetic field components also have a velocity component that points like this. It points out for north and in for south at an angle. Another assumption we're going to make is that this has no net contribution to the net velocity of this entire geometry. In terms of the net motion of this entire geometry, we're essentially just going to ignore it and say that it only goes upward. What we're going to see in subsequent lectures is that this net sideways velocity of these magnetic fields is going to cause this entire geometry to rotate about its central axis. And this is how we're going to eventually describe three-dimensional fields. So we can have vector and scalar representations of velocity, or once again, the net velocity has a direction pointing from the base of the triangle to its tip, and it has a magnitude equal to the number of rows in this triangle. The scalar representation of velocity is simply proportional to the number of quanta in this velocity triangle squared. In order to properly define velocity, though, we need to be able to define spatial and time measurements. So Tetryonics uses a radial relativistically normalized coordinate system, meaning that we take linear distances to the distance that light is going to travel in 1 unit of time. So we can think of this as being a beam of light moving. We say that area is circular, and it is traced out by the diameter made by two opposingly traveling beams of light in 1 unit of time, and that gives us one measure of area. We can also do the same for cubic volumes, where once again we have a spherical volume traced out by 4 beams of light. So this equation here, that c squared corresponds to a circular area, we're going to see on the next slide, is extremely important. It gives us a substitution that we can make inside of equations where we can say, interpret this c squared as an area. So this is going to allow us to very quickly redefine what mass is in Tetryonics. So we have Einstein's E equals mc squared. If we divide by c squared and we interpret it as a circular area, we see that mass is equal to a planar energy density. So it's sort of how many quanta we have inside of a fixed area. Now, in next lecture, we're going to see something called the Gauss-Bonnet theorem in 3 dimensions, but there's a 2-dimensional equivalent where we basically say that because a circle has the same total rotation of a normal vector going around its exterior as a triangle, we can essentially multiply one area by a weighting function to transform it into another one. So we can say that a circular area gives us so much triangular area. Or in even simpler terms, we can say that we can always inscribe a circle about a triangle. So we can also say that this is a triangular area, this c squared. So this c squared, because it's velocity, should normally be a changing area. But what we defined here in terms of this c squared was an arbitrary measure of area. We also described before that these quanta oscillate and that their electric and magnetic fields don't all exist at the exact same time. So what we're going to see soon is that they actually expand and contract in terms of the total area that they have. They start as a vertical line and they expand outward into a triangle and they shrink back in. So we can also define this c squared as being a constant rate of change of area depending on how much energy we have. So we're going to slowly see over these lectures that this c squared means a lot of different things, potentially all at the same time. So we can have to be very careful about the way that we apply math in Tetryonics, where once again this comes back to the idea that geometry is describing what is really going on, and math is essentially just an arbitrary system of logic. So we can use this changing area to define a clock that we can measure time with. So as these quanta expand out of a central line and create a triangle, and then collapse inward, we can use that as a single period to define a single tick of a clock, because time is only ever measured relative to some kind of repetitive event. And this allows us to define a new quantity. Well, there's an equivalent quantity in the standard model that's called quantized angular momentum, but here we are changing it drastically from what it's typically viewed as, and we're saying that this is a literal change in area per second. And we're going to talk about this more later on in the lecture. Now, the rate at which these geometries are going to cycle, we are once again going to assume right now that it is proportional to the amount of energy that they contain. So if we have a geometry with a lot of energy in it, it's actually going to cycle slower than a geometry with not very much energy in it. And this is once again something we're going to justify in later lectures. And we're also going to link this to special relativity and time dilation, and then later on general relativity. So since these quanta have mass associated with them as well as velocity, they also have momentum associated with them. Now momentum in Tetryonics is once again different because it's always a scalar. We don't have a vector momentum in Tetryonics. And the reason why is because of the way that we've defined mass. So we currently see mass in its most general definition as being an energy density per area, or like a planar energy density. What we're going to see is that this corresponds to the inertial mass that is associated with the energies of motion, of matter in motion. Now the actual mass that goes into creating a physical object is something different, and we call it mass matter. So if this geometry describes the energies of motion, matter, as we're going to see later, is a standing wave, but it is still constructed out of the same geometry, but now it's joined into a three-dimensional structure. So when we describe momentum, this mass is actually a composite term. It's the sum of the inertial mass as well as the mass matter. This has a lot of very important implications for particle collider physics that we're going to talk about near the end of the lecture. And this is also what results in us not having a vector representation of momentum. It looks like there's a typo here where we said that momentum squared, or here, said momentum squared is equal to mv squared. We didn't square this m term. The reason why, once again, comes back to the idea that we have to always rely on the geometry dictating what the math is allowed to do. So when we talk about mass, we always talk about all of the mass. It doesn't make sense to define a vector square root mass. So we always talk about mass essentially always squared, and this squared operation essentially ignores the mass term because it doesn't do anything to it. So we now know enough to define what Kelvin calls a kinetic electromagnetic field, or a chem field for short. So a chem field, as we're going to see, it completely describes the energies and properties of matter in motion. Now all matter is in motion to some degree unless it's held at a temperature of absolute zero. So all matter possesses a chem field. What is important to note is that the chem field of a subatomic particle literally exists. It is a real thing that you can measure and interact with, whereas the chem field of a macroscopic object is the superposition of all of the chem fields of its component particles. So we say that we can define an effective chem field for a macroscopic object, but it technically doesn't exist, although the consequences of it technically or effectively existing are still real. Obviously, if you crash your car, you're going to injure yourself. So we can use this chem field to describe the velocity, the inertial mass, the momentum of a particle in motion. We're soon going to see its frequency and de Broglie wavelength, as well as its kinetic energy. So kinetic energy, as you're familiar with, probably is 1/2 times by the mass velocity squared, where once again this mass is a composite term that is the sum of the inertial mass and the mass matter of a particle or a macroscopic object. The reason why this 1/2 comes about, pretty sure this next slide is the correct one. Oh no, it's not. Okay, so the reason why this 1/2 term comes about is because we only associated velocity with the electric field. So only the electric field has a net forward velocity. So when we talk about the energy of this system, the energy of motion is 1/2 because the electric field takes up 1/2 of the total area of every quanta. So that's where this 1/2 sort of comes from. It's not necessarily just a quirk of the math in the way that we do the integral. It has a real physical, property. So as I said, we can use this chem field to describe the de Broglie wavelength and frequency of matter. So in quantum mechanics, matter has actually been proven to be, not just thought to be or theorized to be, a standing wave and have wave-like properties, which is something we're going to talk a lot about in the final lecture when we talk about the double slit experiment. But we can create a frequency out of this chem field. We can take one of these repeating diamond units as being one full oscillation of a frequency component in this field. And we define frequency as being the number of these repeating units moving past a reference point. So what ends up happening is that we have this geometry that is periodic through space, and we create periodicity in time through the fact that this is moving. So as it moves past some kind of reference point and we measure, we experience this oscillation between these different polarities. So one wavelength is equal to the distance from this tip here to this tip here. Now it's very important that, as we're going to see in the last lecture, the wavelength of a particle or even of a photon is not actually equal to the entire size of the photon. And that's going to have a lot of very important implications for this double slit experiment and many other different important results of quantum mechanics. Now, what we know from the Standard Model is that we have this inverse relationship between frequency and wavelength. If we have a high frequency or a lot of quanta, we have a small wavelength. So we interpret that in Tetryonics to mean that these quanta don't actually have a fixed size. They shrink the more energy is put into this geometry. So if this geometry, if we were to add a couple of rows to it, as well as all of its component quanta, will shrink by a certain amount. And this gives us electromagnetic wavelength contraction. So we're now going to recreate the idea of a charge field. Now, this is not going to make a whole lot of sense because electric and magnetic fields are usually distributed through 3 dimensions. But here we have a 2-dimensional geometry describing it. If you want, for now, you can think of this as a single slice, and if we were to rotate it around an axis, we would create a 3-dimensional field. But as we'll see later, that kind of breaks the law of conservation because we essentially need an infinite number of quanta to do that. So we're just going to say that for now, this is a simplification of a much more complicated system, but it is still useful for describing things. So the polarity of this field is once again determined by which one of these quanta is facing up on the outer edge. And we once again have one net electric field for every row. So this charge field is created out of 2 different chem fields facing opposite directions that have equal energy content and size, and they're joined together. How they're joined is through this magnetic zipper that you see going down the center. So we have all these magnetic poles that have opposite polarity that are stuck together, and this rigidly holds these chem fields in place. Now, because these chem fields have equal and opposite velocities, it produces no net motion. That's why it is a static field. Now we can recreate the law of interaction, the idea that similars will repel and opposites attract by overlapping one geometry with another. If we do that, what will happen is that if we have 2 like geometries, these velocity components are going to superposition in such a way to enhance these divergent velocity vectors that we see here. And this is going to create a repulsion on both of these chem fields so that these charges will move apart. If we do that for oppositely charged fields, we're going to enhance these convergent velocity components to create an attraction between these 2 charges. Now, there's a couple of very interesting properties of this description of electric field. The first, and one of the more important ones, is that it has a finite size. This doesn't permeate through all of space. It gets to here and it stops, and there's nothing beyond that. Another additional property that is very interesting is that it is actually constructed partially out of magnetic field components, but all of these magnetic field components have been canceled through this magnetic zipper, and so we cannot interact with them or measure that they are there. But they essentially act like the glue that holds this geometry together. Another interesting aspect is that we said before that these chem fields have 2 sides, and that technically a chem field has no net charge if we talk about both of its sides at once. So arguably, neither do these electrostatic fields. They essentially have no information about polarity. What they have is information about the way that the energy that creates them has been tessellated. So we essentially have two different ways that we could tessellate it, like this or like this. And this produces corresponding interactions depending on sort of like how we permute which one of these two is interacting with each other, whether it's interacting with another like itself or its opposite. And this produces all of our two possible interactions, or three cases. We have negative, negative, positive, 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 negative. So this is something very interesting that we're going to talk about more during the last lecture. The idea that the reason that we have algebraic symmetry in physics is because of geometric symmetry. And like I said, once again, this two-dimensional geometry, it doesn't entirely make sense, but this is a simplification of 3D. And with regards to the idea that they have no charge information, it can still produce the same interaction as long as we always keep straight which side we're having facing up. So we can't necessarily flip only one of these geometries over at once. If we're going to flip them over, we have to flip all of them over at once. And then what we'll find is that if we do that, we're going to get the exact same interaction. It's just that this becomes negative and this becomes positive, or these both become positive and these both become negative. But the resulting interaction is exactly the same. We're also going to talk about the inverse squared relationship for electric fields once we have a three-dimensional geometry for them. So for now, we're just going to ignore it. Now, an additional idea that we have to take note of, and we're going to see again and again and again, multiple times throughout every lecture, is the idea that force is created by the overlap of different geometries in general. So no matter what they are, whether they're an electrostatic field, a magnetostatic field, a photon, or a chem field, if they overlap or any combination of them overlap, some kind of force is going to result as a result of the superposition of these velocity components. This is going to create all kinds of interesting phenomena and new explanation for old ones. And one that we can immediately see right now is that if we had another chem field overlapping with this one, we can say that, if it's facing downward and it overlaps with this, it's going to cancel this velocity component. Say if we just overlap their tip quanta, and it's going to create a net deceleration of -1 for each one of these chem fields. So they'll move one velocity component slower because one of their rows has been canceled. If we move it down again, it's going to have once again -1 velocity, and we can actually create this linear deceleration as a result of these overlapping, which we can use to describe perfectly elastic collisions. In which case it's the chem fields of the particles that are interacting in addition to their electrostatic fields. So we can also create magnetostatic fields as almost the inverse of an electric field, where instead they're joined by these electric field components that have been canceled, and they have an enhanced magnetic dipole, or magnetic moment. So this essentially shows that there are no monopoles in Tetryonics. It's absolutely impossible for that ever to occur in this theory. This also gives us an interesting description as to why the magnetic field is weaker than the electric field. So we can see here that these magnetic velocity components come in and out at an angle, as opposed to these electric field components that come in and out linearly. So when electric field components overlap, they overlap linearly, whereas these overlap at an angle. So they have these horizontal velocity components that have been canceled due to this orientation of these vectors. So when they overlap, we get net vertical attraction or repulsion that is less than what the electric field will produce. So in Tetryonics, this is the reason why magnetic fields are weaker than electric fields. In Tetryonics, we say that the magnetic field is the weak force. So in the standard model, you have the weak force, which is involved in radioactive decay. The weak force is described as being weak because of the idea that most matter is stable and doesn't generally decay. You also have the strong force in the standard model. Now the strong force holds all the protons and neutrons inside of the nucleus, and say that it's strong because it's holding a bunch of positively charged particles in a very tight confined space, and they all want to repel each other very strongly. So it must be strong. In Tetryonics, we say that the strong force is the electric field. So just like we have seen that an electrostatic and a magnetostatic field has electric and magnetic field components that have been canceled, we're going to see later on that particles with a net charge have magnetic and electric components of opposite polarity that have been canceled. And it is the mutual attraction between these opposite polarity field components that actually bind protons together. So a proton has a net charge that is positive, but on certain portions of it, it actually has a negative electric field. So this can bind to the positive sites on another proton, and it's what holds the protons together inside of the nucleus. And like I said, we're also going to link magnetic fields to radioactivity and the stability of matter. So this is the Tetrayonic description of a photon down here on the right. So a photon is a diamond geometry that actually has net effective geometry that is the exact same as a magnetostatic field. In later lectures, we're going to describe why one is a photon and it radiates through space, and why one is a static magnetic field. But for now, we're just going to say that this is unbound and it travels through space. The direction that it travels is actually out of the page towards us. Now, for those of you who feel familiar with electromagnetics, you'll know that we have this electric dipole. So we essentially have an electric field that points like this. We have this magnetic dipole, so we have a magnetic moment that points like that. So we can see that this is actually a transverse electromagnetic wave, that we have the electric field component is perpendicular to the magnetic field component everywhere throughout this geometry. And the result of the pointing vector is once again out of the page towards us. So that's the direction that the photon propagates. So a photon has frequency components the exact same way that a chem field has frequency components as well as wavelength components. As we can see here, we can see the photon propagates perpendicular to the way that we normally see it drawn. During next lecture, we're going to talk about something known as Doppler independent redshift. And that is the idea that as these photons propagate, they actually expand. So we're not going to explain that tonight. We're going to explain that on Wednesday. But this obviously leads to all kinds of interesting and somewhat controversial topics in general relativity and cosmology. And this is essentially part of our assumption that energy is going to expand to its minimum density and seek equilibrium. So now things are going to get very exciting because we now know enough that we can start to construct matter. And we're going to do so based upon two final assumptions, and we're only ever going to make one additional assumption in all these lectures. First assumption is that chem fields can fold into a tetrahedron. Now we're not going to describe how or why, because certain aspects of Tetryonics are incomplete. And as far as I know, this hasn't actually been formulated yet. But if we make this assumption as well as one more, we'll see that it creates all kinds of interesting and cool things. So there are 4 different types of tetrons, and these are described as a quanta of matter. It's the smallest unit of matter that can exist. And it is a tetrahedral standing wave. Now, like I said, there are 4 different types. We have one that is positively charged, one that is negative, and 2 different neutral configurations. So the polarity of this tetrahedron is determined by which polarity of its faces is facing outward. So the final assumption that we make is that the interior faces of this tetrahedron are invisible. We can't see them, we can't interact with them. And so this has a net negative charge. So this has a neutral charge because it has an equal number of positive and negative faces. So if we were to stand far away from this thing, we would measure no electrostatic field. But if we get very close to it, eventually we will sense this positive face. And as we said before, the strong force is the joining of oppositely charged electric field components of the standing wave of matter. So the binding of oppositely charged fascia is what the strong force is in Tetryonics. So we say that these ones, they have a net electrostatic field far away from them. These ones don't, but they will still bind electrostatically if they get close enough. So now we can also define what mass matter is. So before we said mass is a planar energy density in general. We described the inertial mass as being the mass contained in a particle's chem field. So the mass matter is simply the sum of all of the mass in the faces of these particles. And when we describe the inertia and momentum of a particle, we have to include the sum of both of those in the mass term. One additional observation that we can quickly make is that antimatter is matter that has been turned inside out. So it has the same mass, the opposite charge. I'm just going to take a drink of water here. So this is the geometry of an electron. It's made out of 4 negatively charged tetrons. And this is hard to see, but they're bound together by these magnetic dipoles that have aligned in such a way that they go from north to south around the central axis. We're going to see a 3-dimensional picture later on that will make this more clear. But for now, we're just going to have to, well, you can kind of see it here, that they also bind on the outer edge as well as this interior axis. So what's interesting about the electron is that it has 12 external negative fascia, so it has a charge of negative 12. Now this is actually a vast simplification because even though this is drawn as if it has a single quanta for every face, it actually doesn't. If you actually do the calculations, this actually has 1 times by 10 to the 19 quanta in every face. So that's a lot, but it's not very much energy. An additional interesting aspect of the electron is that because it is bound by all these different magnetic interactions so that they cancel each other out, it has no net magnetic field or magnetic moment. And this seems to be in contradiction to the standard model where people can actually measure electrons to have a very small magnetic moment. This is normally attributed to an electron's spin. But this is not interpreted in the standard model as being a literal spin, because simple calculations show that it would need to spin faster than the speed of light to possess as much quantized angular momentum as it should have. We, however, have redefined quantized angular momentum as being something else that essentially allows us to associate the spin of an electron with a real physical rotation about this central axis. We saw before how a chem field has a net magnetic moment across it, and it describes the energies and properties of matter in motion. The faster this electron spins, the bigger its chem field, the more velocity it has, and the larger its induced magnetic moment. And this is the exact same idea that if we have a moving charge, it's going to create a changing electric field, which is going to create a magnetic field. So what we're going to see tomorrow is that the Lorentz transform is actually built into the way that we have constructed chem fields. Essentially, it takes care of that automatically. So in the standard model, we also have these particles called quarks. I don't know if I'm pronouncing that correctly. Some people call them quarks. So a quark is a subatomic particle that ends up creating protons and neutrons. And there are essentially 2 different basic kinds and flavors of each one of these kinds. So we're going to describe what a flavor is near the end of the lecture. For now, we're only going to talk about up and down quarks. So this up quark, it has a net charge of 8. It's made out of 3 tetrions, and there's 2 positive and 1 neutral. So by themselves, they're not all that interesting. So this is a down quark. Once again, it's joined together by the strong force, which is the mutual attraction between these oppositely charged fascia. We have different flavors of down quarks, but we're going to talk about that later. And down and up quarks, in general, join to form protons and neutrons. So this is the geometry of a proton. So it's made of an up quark, and a down quark, just like in the standard model, but because we have a real geometry for this particle, there has to be a specific order, whereas in the standard model, an order is not specified. So a proton has net plus 12 positive fascia, so it has the same amount of net charged fascia as an electron. So therefore, we can say that it has the exact same charge. Now, what is interesting is that in order to have the exact same charge, it has to have the same number of quanta in each one of its faces. Like we saw, the polarity of a chem field on one side is proportional to its number of rows. So in a proton, every face has 1 times by 10 to the 19 quanta. But because a proton has more total fascia, it has a lot more mass than an electron, just like we expect it to. Electrons are a lot less massive than protons in the standard model. So this is the geometry of a neutron. A neutron is made of 2 down quarks and an up quark, once again exactly like the standard model. It has no net charge because it has an equal number of positive and negative external fascia. Now what is very interesting about neutral particles that we're going to talk about for probably the next half hour or so is that they can have a variable amount of mass matter without affecting their net charge, because as long as we add the same amount of mass to every face, even though the polarity of one of these chem fields is proportional to its number of rows, because we have an equal number of positive and negative fascia, we don't change its mass. So we say that in general, neutrons have a variable amount of mass matter. This is going to become very important for determining the stability of different atoms, and it's also going to help drive the process of emission as well as absorption. So we can now start to form atoms. What is this picture? Oh yeah, right, yes. So a proton and neutron, they join together inside of the nucleus. And then we add electrons to it, and it becomes an atom. The way that protons and neutrons join is through the interactions of what we call electromagnetic field apexes. So we can see here that on the back of all of these tetrons, we have a bunch of positive fascia all coming and meeting together at a point. So that is a positive electric field apex. So these produce very strong electrostatic interactions when you get very close to them. And it's through the binding of these electromagnetic field apexes that protons and neutrons join together to create the nucleus of atoms. So we can also see up here there are weaker magnetic field apexes where essentially we have a net of 1 north here and then 1 south. So what is highlighted in this picture is the location as seen from above of these electromagnetic field apexes. What we see here is a deuterium nucleus without its electron. So deuterium is an isotope of hydrogen where isotopes have varying amounts of neutrons in them. As we're going to see soon, in Tetryonics we say that there's actually a 1-to-1 ratio of protons to neutrons in every atom. But what is occurring is that, once again, the neutron has a variable amount of mass matter. And so when you apply the conservation of momentum to particles that go through radioactive decay, you can essentially incorrectly calculate the number of neutrons that was present, because the mass term in momentum is the sum of the inertial mass as well as the mass matter. So this is a picture in 3D. So here we have this positive electric field apex. All of these edges are essentially just a limitation of the software I used to create this. They're not supposed to be there. So this is the electron. This sits in this slot out front. And we can see here that it's joined by the joining of north and south magnetic dipoles around the central axis. Now this electron, as we said before, it has a literal physical rotation that we call its spin. The reason why this electron spins is that, once again, we describe these quanta as quantum inductive loops. So they oscillate between their different electric and magnetic field components. And so what ends up happening is that this electron here is bathed in a changing electromagnetic field. And this causes it to behave exactly like a 3-phase induction motor. Now what is very interesting is that because these neutrons have a variable amount of mass matter, if they have a lot of mass matter, the flux density that this electron experiences is a lot higher than if they have low mass matter. And this causes the electron to spin faster. So this is just exactly like a three-phase induction motor. If we increase the flux change, we get a faster rotation. So this is also what drives emission and absorption. So if we have a photon come in, photon is a changing electromagnetic field. It's going to superposition with the electromagnetic field this electron already experiences, and it's once again going to increase the flux. And this is going to cause the electron to spin faster. In order to conserve energy, we require that the electron absorb the photon into its chem field, where the chem field of the electron in this case is describing the tangential velocity of it as it rotates. So as the electron comes in, it gets absorbed. It initially creates a linear acceleration of the electron away from the nucleus, but because it is electrostatically attracted to the proton, it transforms this into a spin, and it sits there and it spins. Basically like this. Okay, yeah, these are electromagnetic field apexes. Once again, seen from the back is what's going on here. And then, yeah, so now the electron is going to spin. So the deuterium nucleus was changing this aspect ratio there. That's just an error. I didn't crop all the pictures the same way. That's not supposed to happen. So once again, we see that a chem field, it has a net magnetic moment across it, and this is proportional to its velocity. So we can once again, we say that the spin of electron, which creates its intrinsic magnetic moment, is due to a literal spin or a little rotation of its arms about a central axis. So we said before that the neutron can have a variable amount of mass matter, and this determines the rate at which this electron can spin. It actually determines the minimum rate that this electron can spin, and is what creates the emission and absorption spectra of different materials. So as we go up the periodic table, and we have neutrons in higher and higher quantum levels, they have more and more mass matter. And we're going to link this to the radioactivity of very high mass matter content atoms. So it means that these electrons in higher and higher energy states. Now we saw before that chem fields can only grow in odd-numbered steps. Now, the difference between large square numbers of things is very large. It's something very easy to prove. It should be fairly intuitive. The difference between 4 and 9 is not as big as the difference between 32 and, say, like 169. So this is what gives us quantization of the electron energy levels, is this idea that square numbers of energy correspond to equilateral geometries. And so we have this idea that electrons in a low energy state, they easily absorb energy. Electrons in a high energy state don't. And we also have this idea that if we absorb enough energy into an electron, it can eventually jettison away from this nucleus, and we can create beta decay. And then once again, there's an error on the slide where we essentially multiply all the numbers you see here, except for these ones on the left, by 1 times by 10 to the 19, because that's how much quanta an electron has in every one of its faces. We're going to now see that when an electron is above its rest energy, this creates an oscillation in the center of mass of an atom, which creates instability. And this is going to drive the process of emission of photons as well as radioactivity. But first, we're going to recreate a very interesting phenomenon from the standard model known as the Zeeman effect. Now, this is going to become more important tomorrow when we actually see that it has a couple of applications that are actually kind of scary. So, but what we have here is that an electron by itself with no spin, it has no net intrinsic magnetic moment. But what happens is that neutrons and protons do, due to these uncancelled magnetic moments of their quarks. And we also have this extra condition where an electron doesn't necessarily have to join in the slot that is specially made for it between a proton and a neutron. In some materials, they can have an excess of charge, and it can weakly bind here on the proton. So this means that as the electron spins, its induced magnetic moment of its chem field is either going to align or misalign with the intrinsic magnetic moment of the proton. One of these we call spin up, and the other spin down. So in the standard model, we have spin up and spin down. You know that the induced magnetic moment, or the intrinsic magnetic moment of an electron, has two different polarizations. And we know this because beta decayed electrons can be sorted by a magnetic field. We can either push them one way or the other. So spin up is when this induced magnetic moment aligns with the intrinsic magnetic moment of the proton. And we say that this is actually an unstable state for the electron to be in. Because these two magnetic fields superposition, this electron will spin faster than normal, and it will have its emission and absorption spectra shifted upward into a higher energy band. Conversely, a spin down electron will do the opposite. These magnetic moments will cancel, and this electron will spin slower, and it will have an emission and absorption shifted down into a lower energy band. Okay, switch. So the Zeeman effect is when we apply a very powerful magnetic field to a material, and it actually causes this phenomenon where we have a shift in the absorption and emission spectra of electrons in the material into two different bands, one that is higher than normal and one that is lower than normal. So what we can see in Tetryonics is that this is because we have an extra superposition with these already superposition magnetic moments, where we can either increase the velocity of the electron because it will absorb energy from this applied magnetic field, or we can decrease it. So I said before that we're going to connect the rate of spin, or the velocity of these spinning electrons, to stability. So in this case, what ends up happening is that we have one of these spinning very fast and one of these spinning very slow inside of a nucleus, or inside of an atom, because there is generally an equal number of spin up to spin down electrons in an atom. This is going to create a beat frequency inside of the nucleus. So a beat frequency is when you have two different waves, say they're sinusoidal, and they have two different frequencies. The resulting frequency of these two waves superpositioned is the difference of their two frequencies. So the greater the difference, the higher the beat frequency of this composite system. So we know in the standard model that, say, charges that oscillate, and we wiggle them, they emit electromagnetic radiation. So we can actually connect this to emission. All right, but before we do that, we're going to take note right now, in order to talk about this more tomorrow, that in general, very strong magnetic fields applied to matter in general, but more so specific elements, actually induces instability. Now, before we go on to talk about emission absorption, we're going to quickly build a three-dimensional periodic table. So these deuterium atoms, they're essentially an atomic quanta. If we join them together, we increase the number of protons and electrons as well as neutrons, and we can build all of the rest of the elements. And the way that they join together is once again through electromagnetic field apexes. If we imagine that we had another deuterium nucleus that we flipped upside down, we could bond a negative site to a positive site and a positive site to a negative site rigidly. So essentially, if we just do this, as well as a bunch of trial and error that we're not actually going to do tonight, because Kelvin already did and it took him a couple of years, we can build this. So this is what Kelvin calls the periodic table 2.0. So this is very confusing and complicated at first. So we're going to start down here at the bottom right. This is element 120 viewed from the outside and viewed from the side. So element 120 has 120 protons. So going up from the bottom to the top here, this is the first quantum level, or quantum shell, and this is the second, and it goes all the way up to the top. So that's what these rows are. And we said before that these neutrons have a varying amount of mass matter that increases as they go up in quantum level. And like I said, we're going to connect this to radioactivity. Within each row, we have different electron orbitals, and that is what's being shown in the center here. So this center picture is actually this row taken out of here and then viewed from above. So we have all of the familiar electron orbitals where we start with S, because they're all color-coded. So this is S1 and S2. Then we have P, which is around the outside, and then D, which is the green, and then F, which is around out here. So this is sort of an exploded view of all these quantum levels and shells. And as we build the periodic table, these shells and quantum levels are filled up and out, so that essentially this atom remains approximately spherical as we build the entire periodic table. And all of these S, P, D, and F orbitals are filled in the same familiar fashion, where we fill this one, which is S1 and 2, and this one, which is S3 and 4, I think it's called. I might be mixing up the names and the numbering. And then we go to P, and then to S again, then P, D, and so on and so forth. And what I'm going to do is I'm going to show a YouTube video that describes this much better than I can using pictures. This is essentially the periodic table being iteratively made as we add more and more atomic quanta to it. So this is our exploded side view, and this is the atom seen from the outside. Okay, so like I said, the neutrons, they have varying mass matter. As we go up the periodic table, they gain mass matter. It increases the spin rate of the electrons, and this actually creates instability through two different ways. So the first way is through the electrons. We can calculate the, oh wait, no, sorry. Before I talk about this, I want to show something interesting. So what you might have noticed is that these electrons are switching their orientation as we build the periodic table. And basically what is going on is that in order to bind new nuclei to this, we need to keep switching their orientation, because we saw before those electromagnetic field apexes. So some of them need to flip upside down depending on how we're binding the next one. So what is going on is that this periodic table actually obeys the Pauli exclusion principle. Now, the Pauli exclusion principle is this idea from the Standard Model that we can't have two electrons with the same spin in quantum state in the same orbital at the same time. So basically, if we have one spin up electron in an s orbital, we have to now have a spin down electron. So what this does is this actually helps maintain stability in the atom. So we can calculate the center of mass of a system of masses that are revolving around a central point. And what we can very, very easily show is that there is less oscillation if they spin in opposite directions than if they spin in the same direction. So if they have equal mass, we can essentially calculate the center of mass of this system of two particles as just being the central point between them relative to our arbitrary x-axis. If they spin in the same direction, the center of mass will travel around in a circle with them. And so we'll have a maximum amount of oscillation in two different sort of like degrees of freedom. If they spin in opposite directions or revolve in opposite directions, this mass will simply go up and down. Now we can essentially extend this system, obviously, to an arbitrary number of masses with the same revolution. And what we can do is that if they all revolve in opposite directions relative to each other, and we introduce a phase delay between one pair and another, we can start to cancel this center of mass oscillation by adding more and more masses so that it eventually gets very small. So that is essentially what occurs inside of an atom and why it obeys the Pauli exclusion principle. Now, it's not exactly a reason why, it's kind of just sort of like a cosmic coincidence that it occurs that way. That we kind of attribute to one of our initial assumptions that energy wants to expand and seek equilibrium. Now, depending upon the number of protons and electrons inside of a nucleus, we might not be able to cancel this oscillation of center of mass as well as we would normally like. So even though I currently don't have proof of this yet, something that I'm kind of working on, What I would like to eventually show is that, and what is probably true, is that this is what helps determine crystallographic structures. That if we extend this now to not just multiple electrons in a single atom, but multiple electrons in multiple atoms, depending on how we orient them, we can minimize the oscillation per cell. Now we can connect this rate of spin to emission, where before we essentially, I didn't describe this, but we implicitly assumed that they were revolving at the same rate. If one revolves drastically faster than the other, then once again we create a beat frequency. The more quickly it revolves, the more the center of mass is going to move up and down, and it might start to move side to side as well. So we get this kind of chaotic oscillation in the center, the bigger the difference is. So once again, we know in the standard model that oscillating charges emit electromagnetic radiation. So this is the way that we describe emission in Tetryonics, is that when the center of mass of an atom, because it has positive and negative charge components in its electrons and protons, when it oscillates, this corresponds to emission of a photon. When it oscillates above its rest oscillation. The higher the frequency of the oscillation, the higher the frequency of the emitted photon. And once again, we know that high frequency corresponds to high energy. Now once again, in the standard model, we have this condition where an atom is stable if it has about 1.5 neutrons for every proton. And what is important is the way that this was discovered was once again through the conservation of momentum, as far as I remember from reading about this, due to radioactive decay, and they can also do similar ideas in particle colliders we're going to soon see, in order to infer the existence of neutral particles. Because it's very important to note that you can't actually detect a neutral particle the way that you can detect a charged particle. You can actually track the path of a charged particle. This is how you get all these curvy pictures of particles going through an accelerator detector. But you can only infer the existence of a neutral particle or its creation through a radioactive decay process through applying conservation of momentum to the path of a charged particle where its path is abruptly changed and there is no apparent reason why. So we infer that there was some neutral particle involved in interaction there or was created through radioactive decay that caused that change. So once again, in Tetryonics, we say that this is, I guess, is kind of a loophole for Tetryonics to exist. We say that that's not descriptive or specific enough. We can do the same thing by saying that these neutrons have a variable amount of mass matter. And you can't stop us, basically. So once again, because these neutrons have a variable amount of mass matter, because we said before that these quanta are quantum inductors and they oscillate, what ends up happening is that we don't only require favorable spatial orientation to create the strong force, but we require a phase match between these interacting particles' fascia. We also said before that the rate at which these geometries cycle is inversely proportional to their energy content. If they have a lot of energy, they cycle slower. So in general, there is a phase mismatch between the neutrons that are in a low quantum level and the neutrons in a high quantum level. This causes a different kind of oscillation in this atom's center of mass that can correspond to emission. Excuse me. So because these neutrons have such a higher mass matter content than protons and electrons, when they emit a lot of energy. They emit gamma rays, essentially. And that's basically off the scale in terms of electromagnetic radiation. If the oscillation gets bad enough, it can also create all of the other decay processes that we're familiar with, where we can have electrons jettisoned, we can have neutrons and alpha particles and protons all come flying out of this nucleus as it essentially shakes itself apart. That's the wrong direction. So these neutrons, they essentially also have energy levels. So not only can the electron absorb energy due to incident photons, but so can a neutron. Because once again, it's neutral, so if it gains energy, it won't change its charge. So it's kind of a wishy-washy explanation. We essentially say that it happens because it correlates with previously known knowledge, and there's nothing stopping us from saying it happens. But like I said before, part of this theory is still sort of under construction, so essentially it is what it is. But like I said, it already creates what we already know, and does all sorts of other cool stuff, so why not? So we have two final topics in this lecture, and the first is particle physics. Well, particle colliders, and the reason why tetrons have never been discovered. So first we need to just talk a little bit about particle colliders and the way that they work and the way that particles are even detected. So a particle collider, you're probably familiar with, it accelerates charged particles, usually as a result of turning matter into plasma, where they apply a very high frequency electromagnetic field, or they heat it, it becomes charged. They contain it in a magnetic field because a moving charge will experience a force due to a magnetic field. They accelerate it in a gigantic racetrack close to the speed of light. Two streams either collide together or collide with a stationary target. An subatomic explosion basically results, and all of the pieces of these particles and atoms come flying out. And if they are charged, they can be detected. Now, the way that they are detected is through the photoelectric effect that was discovered by Einstein. Okay, let's say like photoelectric effect, you have this charged plate, a charged particle comes in, it interacts with the charge there, or it can be a photon. It knocks the electrons off the plate, some of them, not all of them, a few of them. What you do is you put another charged electric plate behind this one. The particles, or the electrons that get knocked off, they go and they knock off more electrons. So if you put a gigantic cascade of these charged plates, you create this pulse of electrons that eventually becomes a measurable current. So if you make this extremely tiny, and you put a gigantic array of them around where you know you're going to collide with beams, you can track the path of these particles through space. Normally they move extremely fast, so they put something called scintillator, which is a special material that kind of slows the particles down. They also put a gigantic magnetic field over the detector. And once again, the magnetic field will create a force on a particle that is going to act perpendicular to its direction of motion, and it's going to make it travel in a curve. Because if it travels in the curve, it takes longer for it to get out of range of this detector, and they can track its path. Now to continue this explanation, I need a picture. Okay, so that is basically what you're seeing in this picture. These are the tracks of charged particles, and because of the magnetic field, they come out and they move in a spiral. There's a lot of curvature to this spiral, then they don't have a whole lot of inertia because they're easy to accelerate in a new direction. They travel very straight, they have a lot of inertia. So what scientists typically do in order to characterize particles and say that they are unique is that they classify them based upon their mass to charge ratio. Now, we can potentially already predict that there's a gigantic problem with this if Tetryonics is true. And that is that when we calculate the inertia or momentum of a particle, it is a composite term of its inertial mass and its mass matter. So one particle with, say, the same amount of charge can look like a different particle with the same amount of charge, but they can have a completely different standing wave structure. And the only difference is their mass matter content or their inertial mass matter content, or their inertial mass constant. So tetrons, coincidentally, once again, they have the exact same net charge as a quark. So with enough inertial mass, they can look exactly like a quark with this detection method. And so far, I don't know of any way that this is able to be fixed. Now, once again, neutral particles, they can't actually be detected. If, say, we had a curve and all of a sudden it curved a lot for no apparent reason, we would infer that there was a neutral particle created as some kind of decay process that shot out in order to cancel this one's new momentum. So since we just apply the conservation of momentum, once again, the problem with that is that the mass in the momentum term is a composite term, and neutral particles in Tetryonics can have a variable amount of mass matter. So they could either be extremely massive in terms of its mass matter content and moving slowly, or it could be moving very fast and have a very low mass matter content. There's no way to tell. So this is kind of a huge problem, not necessarily for Tetryonics, because as we see more and more and more as it creates more and more of the standard model with the same predictions but a different mechanism for doing so, that this is kind of a problem for particle physics. And if this is true, what it shows is that essentially the last 70 years of particle physics and a good deal of quantum mechanics was essentially, unfortunately, a waste of time, basically. And that the Large Hadron Collider is a $10 million hole in the ground. Now, this is the way that we describe different flavors of particles in Tetryonics. So particles are typically described as having an energy, and that's once again because we kind of don't really know if it has a high velocity or a high mass, so you talk about the kinetic energy and the momentum of the particle. So if we have, say, like a down-up quark, what has happened is that this down quark has a gigantic amount of inertial mass compared to an up quark, to like a regular one. And so that's why it has a higher energy. I'm just going to take another drink of water. That is true of all of these other different flavors of quarks. The same particle with a different amount of inertial mass. Now, what we see over here is what physicists call the particle zoo. So these are all the supposedly unique particles that have been discovered over the last 70 years of doing experiments in particle colliders. So Tetryonics predicts that the majority of these don't actually exist. These are the only particles that exist. Essentially, we have up quarks, we have down quarks. These are obviously different flavors, but it's just that they have more inertial mass. This is a positron, this is an electron. And these are, once again, essentially heavy positrons and electrons. And these are all the different types of neutrinos, once again with varying amounts of mass matter, as well as potentially inertial mass. It's impossible to tell what is going on with neutrinos because they're neutral. So you may have heard of the idea of neutrino oscillations, that neutrinos can change between their different flavors over time. So Tetryonics predicts that they do change, but they only change one way. They only decay from high energy to low. They don't actually oscillate back. And then once again, we have the mesons here, which are just two quarks joined together, and all the baryons, protons, neutrons, antineutrons, and antiprotons, and as well as these tetraons. So the final topic that we're going to discuss is uncertainty. And for those of you who know about quantum mechanics, this has probably been something you've been wanting to ask about this entire time. What about uncertainty? So in Tetryonics, we have a completely deterministic model of quantum systems. Well, we know that in real life, quantum systems have this property of uncertainty. So basically what this says is that the precision that we can know a particle's momentum, or even say a system of particles, and the position of a particle, or where all these particles are in the system, the product of this is a minimum. So if we know the precision, if we know the momentum to a high degree of precision, we can't know its position. And there's also a corresponding relationship between energy and time. So what we can show is that, amazingly enough, Tetryonics actually is subject to uncertainty. But once again, through a completely different mechanism than what is normally described in the standard model. So first we're going to, in general, describe this idea of uncertainty. And it originally arose solely out of math, created by this guy, Werner Heisenberg. We're not going to go into that much detail. We're essentially just going to describe it by an analogy that this same guy created. So he basically said that if we have a UV microscope and we want to see an electron pass by underneath it, we could shoot a photon with a very high frequency and high energy content at this electron. It'll bounce off, come back, and we'll see where the electron is. But in doing so, this photon is going to impart a small amount of its momentum to the electron and sending it shooting off in some kind of direction. So if the photon has a high energy, even a small amount of energy imparted to it will send the electron off flying very fast, and we correspondingly will not know its momentum very well. But because of the very short wavelength of our high frequency photon, it can bounce off very tiny features of the electron, and we can know its position very well. We could also do the opposite, where we put a very low frequency, very high wavelength photon, and we bounce that off the electron. Because it has a large wavelength, we won't see the electron very clearly. It'll kind of be fuzzy, and we won't know its position very well. Because this photon also has a low energy, when it bounces off, the small fraction of energy that is imparted to the electron as momentum is small. And so we know that the electron's trajectory is not going to be altered very much, and we will know its position very well. So this analogy, for now, is going to have to be good enough for us, because as we're soon going to see, this uncertainty is a result of, well, in our system, in Tetryonics, we can show that it is a result of using discrete geometries for energy, and the idea that we can only create forces which correspond to a transfer of energy, which corresponds to a measurement, as a result of overlapping them. So normally, in a lot of different theories in the Standard Model, uncertainty is associated with randomness. That it's not, because we can't not just measure a particle's position and momentum to any arbitrary level of accuracy, but because this originally came out of math, we also can't calculate them. That essentially stuff can happen, essentially anything can happen while we're not looking, which is kind of a crazy result, because it is. So there's this idea of imaginary particles in particle physics and in quantum mechanics. The idea that, wait, I should go back a slide here. Because we have this uncertainty relationship between energy and time, is that theoretically we can have a particle just pop out of existence for absolutely no reason, and as long as it doesn't have a lot of energy or exist for very long, then technically it didn't break any rules or laws of physics, and so everything is okay. So this is essentially used as a band-aid solution to describe force transfer in particle physics. So one of the particles that is thought to exist is something known as an exchange particle. And the idea of an exchange particle works like this. If we have two people standing in boats and the water is very calm and there's essentially no friction of this boat on the water, and this guy, he throws a sandbag at this guy. What's going to happen is that his boat is going to recoil away from this interaction due to the conservation of momentum, and when this guy catches it, he is going to travel in the same direction that this bag was thrown. And so this is the idea of an exchange particle, that when particles say they have an electrostatic interaction, what happens is that an exchange particle literally hops from one particle to the other, and it produces the resulting acceleration. So photons are thought to be the exchange particle of electric fields. So say, for example, an electron, we see here in the center, is surrounded by a cloud of virtual photons. Now these photons essentially pop into and out of existence all the time. Once again, for absolutely no reason. There's no justification for that as far as I'm aware, other than the uncertainty relation. Now in Tetryonics, we know that force is created by overlap. When we overlap one geometry with another, it creates the resulting force. So in Tetryonics, this region of overlap is essentially our version of an imaginary particle. But once again, it's not exactly like a physical thing. It only exists once we overlap, so that's sort of how it pops into existence. Now, another important aspect of quantum mechanics is, as a result of the uncertainty relationship, is that the uncertainty relationship, of course, comes out of math. And it comes out of the idea that particles are described by a wave function. So whenever we take measurements of, say, like a particle's position or state, what we get is a probability distribution of where it is likely located. Now what we can show is that our chem fields that we have described are actually connected to statistics and probability, and they have all the same properties as this probability distribution. So the most important distribution in statistics and probability is the standard normal distribution. So this is normally drawn as some kind of bell curve. But what we can show is that these chem fields actually create the standard normal distribution, even though they appear to only approximate a bell curve. So we have this mathematical theorem from statistics to say that if z, which is some kind of distribution, is a standard normal deviate, then x equals z of sigma plus u will have a normal distribution with expected value u and standard deviation sigma. Or we could say that if x is a general normal deviate, then if we rescale this x distribution, we'll get the standard normal distribution. Now we can show that these chem fields are a general normal deviate. So we had this distribution that we took note of before, where we go from 1 all the way up to the number of rows, then all the way back down again. We can take this as a probability or a statistical distribution, renormalize it, and show that it gives us the average and standard deviation of the standard normal distribution. Which I'm fairly certain there's only one distribution that has an expected value of 0 and standard deviation of 1, and that is the standard normal distribution. What's going on here? That didn't open correctly. So I'm going to show you an Excel file here. And what I've done is I have treated this sequence as a statistical distribution. So here I calculate its average, and I use that to calculate its variance. And then I use that average to now calculate its standard deviation. And I use these two values to rescale it like we saw in that previous equation. Just quickly go back. That one. So I get this rescaled sequence. If I calculate the average and standard deviation of this, I get basically 0 and 1, which only the standard normal distribution is supposed to have that. So we basically can say that this is the standard normal distribution, even though that is completely unintuitive and it doesn't look anything like it. Now if we go down, I do this for various n values, which is the number of rows, and what we'll find is that I keep getting the same answer for as low as n equals to 3, 1 and basically 0. We go back up, we do it for 4, 1 and basically 0, 5, 1 and basically 0. So what that tells us is that these chem fields are normally distributed throughout space. But that by itself is not good enough to recreate probability and statistics the way that we would need it to, nor to recreate quantum mechanics the way that we think it should be created. Like I said before, force is created by overlap. A force produces an acceleration, which produces a change in energy, and a change in energy is something that we can actually measure. And we're going to see more of this in later lectures, why we can only really measure a change in energy. Basically, it's simply, in terms of electronics, it comes down to the idea that we're measuring changes in current and voltage, and that is essentially a change in electron energy. So what we need to do now is show that our measurements are normally distributed through space. So what I did is that because these quanta are equally subdivided into 4 components, you can calculate the total fractional area in this region of overlap that has essentially been completely overlapped. Then we say it has been canceled. And this is going to cause some kind of acceleration. Like we saw before, if we cancel 2 full rows, we get a deacceleration on these chem fields of 1. So, like I said, we can sort of feel one geometry with another by overlapping it with different offsets and sort of like going deeper and deeper into this geometry. And if we do those calculations, where once again this is sort of like we overlap with only 1 row, but it only has half of a quanta canceled. Then we go say deeper, and then this is a certain offset. with certain depths, and this is a certain offset at certain depths, and we get essentially these different distributions going along to the left. And then what we can show, where did it go? Oh, okay, right. Can show is that we get an average of basically 0 and a standard deviation of 1. That's for this one. I think the calculation up there is missing, but if we go down to here, once again we get the same thing. This is basically 0, and this has a standard deviation of 1. Same thing for this one. And that one. So now we've shown that not only are these chem fields by themselves normally distributed through space, is that if we measure them with each other, which we are restricted to doing because everything is constructed out of matter and it all has the same components, we're going to get a normal distribution of our measurements. And so we create the idea of a probability density function describing a particle's energy of motion and even its position. So this gives us the result that, once again, uncertainty has absolutely nothing to do with randomness. That is a result of using real physical objects as representative of energy. And obviously, if Tetryonics is true, and we're going to see over the next couple of lectures different ways that we could actually test it, then it shows that energy is a real physical thing with properties, and the tessellation of it creates stuff and gives it its properties. So that's it for this lecture.